Welcome to A2 Physics. Today, my name's Steve Jones. Today, Jane Owen is going to go through data analysis part 2.
Right, hello, and it's good to be here again and talking about data analysis part 2. I was going to look at log relationships this time. Last time we looked at lines of worst fit and how to get the gradients. This time I want to look at the log relationships, and if I have time and I finish this part, then I'll go back to what we didn't quite finish last time because there was quite a lot to do. Okay, so if I've got this exponential relationship here, C equals K D to the N, it's an exponential relationship because I've got this power term. And what physicists like to do is they like to put it into the form of y equals mx plus c, because they know if they can get it into that form, they'll get a straight line and they can get a relationship between the two quantities. Now here, the two variables are the count rate and the distance. So that's this bit and this bit. If we want to get it into y equals mx plus c, and you see this exponential form, then what we have to do is log the relationship. And because it's not to the base 10 at all, i.e. this d varies, then we do natural logs, okay? So log c equals log k. Now, when we are logging a multiple, then we add those two log quantities when we do it. So log d to the n, but this n here comes back down to ground level and we times it by the log d. So we get log c equals log k plus n log d. Now this is into the form of y equals mx plus c, but before I relate it to y equals mx plus c, let's just rearrange that equation. So I've got log c equals n log d plus log k, and then I can more easily relate that to y equals mx plus c. So to get a straight line then, we plot log c on the y-axis and log d on the x-axis. So we get something that looks like this, log c, log d. And we have there that the gradient m is equal to n. Take a nice big gradient. So m is equal to n, the constant. And this y-intercept here, little c, not to be confused with big C in this case, is equal to log k. So if we had to get log k out by using the y-intercept, as long as x equals 0 here, and we can read it straight off, then we would do e to the c equals k, because what we're doing was anti-logging this in order to get k, that constant, out. Once you've got this constant, and once you've got this n, you can put it back into this equation here to get a value for k and n, which is the relationship between c and d. And that's the whole point of doing this. So let's have a look at a few logs, all right? And how do you express logs? Okay, well, in practice, okay, if you've got the raw quantity, let's say this time it's x, in 3 significant figures, then it should follow that the log quantity has got 3 decimal places, okay? So again, here, 3 significant figures, and it should be 3 decimal places, because you can see that the 3rd significant figure has a change and a bearing on the 3rd decimal place. Now it should go row by row, but I know that WJC sometimes likes it kind of like a little bit more uniform. So here a candidate has got 2 significant figures here. They've logged the quantity, and quite rightly they have ignored any unit in the log quantities, because a log quantity doesn't itself have a unit. What you're logging may have a unit, but the log of that quantity doesn't have a unit. And what we have at the top of the column heading usually has to relate to the calculated quantity and not the actual what they're logging. Okay, so there's two significant figures here, and all of these have been quoted to 2 decimal places. So that's consistent. And I've noticed that WJC will allow this, even though this is 3 significant figures and this is only 2 decimal places. It's all tidy because the majority is 2 significant figures to give you 2 decimal places. So they kind of like, you know, made them all the same. That's fine. Okay, but if you did do 3 decimal places, that would still be fine, but it's probably better to do it all the way down. Okay, just be consistent row by row. Okay, all right. Now have a look at these 2 graphs. All right, and have a look, see what you think about them. So that first one there, you can see the points here. There's 1, 2, 3 points here, and there's 1 slightly under the line, and there's 2 on the line here. So what the candidate's done is he's joined up the first and the last, and he hasn't actually considered the distribution of the points about the line along the whole length of the line. So I think that actually there should be a little bit of a shift to that top top left corner, all right, because you need an even distribution of points along the entire length of the line. Okay, what about this next one? What the candidates have done here is they forced it through an origin, even though that is a false origin. The candidates decided to force it through that origin, and you don't want to be doing that. You want to be following the trend of all the points there. And you can see that there is 3 above the line, there are 2 below the line, and if you just twist it around to give a better fit, judging that the points either side of the line along the whole length of the line to give a better fit. The question is, could you do a better fit? And we'll have a look at a few lines now. Okay, is there anything wrong with that? Now, this one was used to get the Y-intercept. The Y-intercept would be here, but not in this case, because x is not equal to 0, and you can't just read it off. So what you would have to do here is find a known point. Let's say this point here, an x, y. You would have to find the gradient by doing your triangle and doing dy by dx to get the gradient. And then you would have to substitute all of this into y equals mx plus c to get your value of c. And rearranging that, you would do y minus mx. Don't make the mistake that some candidates do, and they go and they take it across and it's divide. No, it's take it away, all right, when you take it over to the side, equals c, all right? So you would have to do, so x is known, y is known, m you can calculate, and you can work out your c. You cannot get it off of that graph when x equals 0, all right? Okay, so let's have a look at a few graphs that some of my pupils have been doing. It's good that log D and log C are nicely labelled up. No units, of course, in the log quantity, but you can see here that there is a compression, easy mistake to make when you're first going out and doing these graphs. Compression of the y-axis, but there's also compression of the x-axis. And what you want to do is kind of like expand that. So you could start, say, at 2 and go to 2.5, 3, 3.5, 4. And that would mean that you can literally double your scale or double where the points are on the axis. So it's a better sizing fit for your axis. You're always considering the first and the last and seeing how many squares it is going across. 1, 2, 3, 4 up. You see that one's just inside that 4th square, and you can easily double it because these squares are 12 up. So at least you can double it to 8 at least. Okay, so we say that's compression. I also think that there is unless you're going to identify that that is anomalous because it's off the graph, all right, and only identify one as an anomaly, you don't want to be doing any more than that, then I actually think that this line should be twisted to give a better fit. You don't have to identify any anomalous points if you honestly don't think that they're anomalous. But if one is slightly out, then the line has to reflect. It's got to be the best fit of all the points either side of the line along the length of the line drawn. And that would need a little bit of a rotation. It's probably the hardest mark to get, that line of best fit. Have a look at another one. I just kind of like put in here where the points actually are, and then you can decide for yourself whether that is the line of best fit. You have to say to yourself, can I do a better line of best fit? And I think you've got one up here on this side, you've got two down towards the bottom, and then this is smack bang on the line as these two are. So I actually think that this needs rotating ever so slightly, and this poor candidate has actually done that and then rubbed it out and then repositioned it. So he's been trying to kind of like place it. And I have to say, it is really hard, you know, to judge where that line of best fit is, first of all. So just get an idea of looking at others to see where, you know, where is the best place. But what's nice here is he's got his axes here, and he's even shown the working of the read-offs to get the gradient, which is, you know, even though it's not negative in the working, it doesn't matter. At least he's showing what the read-offs are, because that's what you'll get your marks for. Okay, all right, so that kind of like gives you some ideas of drawing graphs. And we've related the gradient, the y-intercept, back to the equation given. I just want to check. This second graph here, yeah, they've done that, yeah. Okay, let's move on then. Okay, another, because we've related, because once you get your gradient, by the way, gradient here, he's shown the triangle nice and big, okay, and you can relate that back then. Once you've done the gradient, you can relate it back to your equation that we've done here and relate it to n, okay, so m is equal to n, all right? And then you can do the same for the y-intercept, whether if there's a false origin, you're going to have to substitute it into the equation. Okay, right, let's carry on then to another log relationship, just to see if we can do it. So h equals km to the n, log natural h equals log k plus n log m. Rearrange it so that you can directly relate it to that y equals mx plus c. Okay, and then the thing that's changing here is the mass. Oh, what have I done? Okay, I've done something. Let's go. Oh, I can't bring it over for you. I have, sorry, I can't bring it over. Okay, I've got half a screen to work with. Okay, let's just carry on as we are on half a screen. I apologize. I think you can see that. It's just for me that it's half a screen. Let's see if I can bring it over a little bit more. Ah, that's better. Okay, right. So what we're changing here is the mass, and we're also measuring the depression. Okay, so we can plot y log h and log m along the bottom, and we will have, it's good to ring these, or you can state log m on the x-axis. You know, be specific, all right? That's what they want to see, all right? Log h on the y-axis, and then say n is equal to the gradient, c is equal to log k. But that's still not enough, because if you want to work out what k is, anti-log it, e to the c equals k, all right? So n equals gradient, and the y-intercept there, c equals log k. All right, so it's a similar sort of thing. Okay, so here we are. We've got some readings here, and we've got the mass, and we've logged it. Now here we've gone to 3 significant figures. That's okay. WJC are happy with that, even though strictly speaking it should be 3 significant figures to 3 decimal places. All right, but you won't be deducted any marks. H here, 2 significant figures, so 2 decimal places, and really there's only one that is 3 significant figures, so that's okay for this to be tied in with all of the rest. That's fine, and they won't take any marks away. All right, have a look at this graph here, and look, no, there's a unit for the mass and for the height. Okay, there's no repeated readings. That's my fault because I made a video for pupils and I should have done it twice for them. But you know, remember to do repeats where if you can possibly do repeats. Log m and log h, they have no units, so you can write it log m or log h, or you don't have to have that bracket there, but it shouldn't really have a unit there. Okay, right, look at this graph here. He's forgotten the scale, so he's forgotten the log, whatever it is on the y-axis and x-axis, he's forgotten to label them, so that's -1 mark. But he has got a really nice size to all of his plots, so that's good. But you know, 1 is just above the line up here, 1 is below the line here, and you have to ask yourself, can you draw a better line? And I think you just twist it ever so slightly, even just 1/4 of a square, and it will give a better line of best fit. You are trying to draw the best line of fit, right, in this case. Okay, so now you can see here that x is not equal to 0, so you cannot read this off. So this candidate here, he's related the fact that n is equal to m, which is great. He's even shown the read-offs here into the working dy by dx, which is great. The problem is he has not shown where that triangle is. So that's not good enough. So he's taking, you know, you really do need to put a very large triangle in place, because the examiner at the end of the day has got to be checking these read-offs, and they've got to be checking that the read-offs are from a triangle made big from the graph, and he hasn't got that triangle, so that would probably be worth 1 mark or 2 marks out of a possible 3, just because he didn't draw a very large triangle on his graph to take the read-offs from. Okay, now what he's also done here, he's identified that log k is the y-intercept, the point that crosses the y-axis. But he's read it off, and not only that, if we just expand it a little bit more here, 0.25, 0.5, 0.75, or 6 point, no, 0 point, that's it. But he hasn't read it off correctly. So not only is it a false origin, but they haven't read it off correctly either. So it's kind of like a double whammy. You won't get any marks because he will have to find a point x, y that fits onto the line. So any point will do. You can make one up. All right, just mark that there. Okay, so he could have gone with something that is, you know, very easy to read off, and then substitute it into y equals mx plus c. All right, he's got his gradient from before. He can put in his values of x and y. He can rearrange it to get his y-intercept. Okay, all right, so it kind of, you know, you've got to be really, really careful. The other thing that you've got to watch is the plotting of the points. Now, the plotting of the points have got to be to the nearest half a square. All right, okay. All right, now moving on, I think this kind of like follows on from one of the questions and you know, candidates had to kind of take a value of B and a D, and they had to show their working, and they had to show their repeated values. So where possible, and you have to take repeated readings, show that you have done that. Don't assume that you can just put the average down without showing what the repeated readings are, and always show your readings to the resolution of the instrument that you have been given. So if you have been given a ruler to read it to the nearest millimetre, then you have to quote these all to the nearest millimetre. If you've been given a Vernier scale, a manual one will read to the nearest 0.01 of a centimetre, so the nearest 0.1 of a millimetre. Okay, but it changes if you've got a digital one, by a factor of 10. It's a bit more accurate, greater resolution of the instrument. So always go to whatever they say their resolution is. So if they say they've got a ruler that can only read to a centimetre, then you will be quoting it to the nearest centimetre, and you won't be putting millimetres in. So always kind of like be mindful what the resolution is of the instrument. So these are all same resolution, and repeated readings are given. Okay, now we don't have to deal there with lines of worst fit to give you uncertainties. So I'm going to go back now, I think. Are there any questions, Steve, in the forum at all, or in the chat about logging and those? Because otherwise I'm going to go back to...
Yeah, I just got one simple question. Do you have to use natural logs, or can it be any log?
Okay, right. If you've got a value up here, okay, and you don't know what this value is going to be, i.e. if this value was in tens, then you could do log to the base 10. So if I were you, I would just use natural log, because this m value will always change, and usually this is the value that does change. You could have a graph that's a semi-log graph, so that there will be log on one side but not on the other side. But I would just use natural, and I'm sure that's what you said. Is it, Steve? Yeah. Okay. I mean, all right. Okay. So I'm going to go back to, I think I'm going to go back to what we did, and spot the mistake here. This is what we did in the first session, okay? And we got up to red, all the red. This is what we covered. So you can go back to the first one to kind of like have a recap on all of that. But what I've done is we got to a certain point and I carried on in green. So here we go. Here's drawing a line, just drawing any line. This is drawing a gradient on a line. You can see here that this is going to be too small. I know some of you are going to say, but it will give me exactly the same number whether I did it small, medium or large. But the accuracy of that number that you take will be so much better if you can take a gradient from a larger part of the graph that you have drawn. Okay, and that doesn't mean to say that if you've got the first point and the last point, okay, you don't have to limit your line to those two. Just draw it across the whole graph grid. Then you've got yourself the choice of a nice large triangle that you can place and make your life and the examiner's life a lot easier to mark. Now this candidate here, he's joined his triangle up to 2 points that actually are in the table, but they don't lie on the line. So this is not going to be good enough, because what you want is you want 2 points that are on the line. So you are going to have to take 2 points, and I would literally take these two, but be careful about taking that last one, because you've got to check that it is 0 here, or just make sure you read it off properly. Okay, Always good to write the read-offs here, 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 and then you can transfer them to your working, all right? Okay, so what this candidate has actually done, he actually hasn't probably drawn a triangle like this. He's just taken 2 points from the table and then not realised that those points don't actually sit on the line of best fit, which is actually not what you want, because you want to get the gradient of the line of best fit that you have drawn from all of the points that you have got. And it might be that none of the points actually fit on your line of best fit. Okay, right, so I went very briefly through. So if you have drawn your line, and I think I'm coming now to worst fit lines. I'm just wondering if I've got an example to show you. Is there one? Yeah, here. Okay, yes. So I did look at this last time, didn't I? A little bit. Okay, so here is a really nice graph here. It's labelled up. It's a nice distribution of points. I would probably argue that the points are over half of the graph grid available in the Y direction and the X direction. So there's a nice spread of points, okay? And the worst fit line, you take it from the bottom of the bottom to the top of the top, all right? But this one here is the limiting one that you would have to bring the line down to, because both lines should fit through all of the error bars there. Now, if you find that one is off completely, then you can circle it and call it an anomaly, all right? But in this case, where the candidate has circled it, I don't think that's an anomaly at all, because the points do go through the line of the error bars, okay? So once you've got those 2 lines of worst fit, you've got the steepest and you've got the shallowest. Now you have to go about trying to get the uncertainty in the gradient. So you've got yourself 2 triangles here, and you know you've got just be careful with the read-offs. Put the read-offs where you can access them easily and where you actually read off from the graph, all right, and then kind of like put it into your working, all right. And then the uncertainty in the gradient will be given by whatever the gradient is of the shallowest, take it away from the steepest, and then divide by 2, and that will be your uncertainty in the gradient, all right. And then taking that forward, not in G but in the gradient M, taking that forward, then you don't draw yourself a line of best fit. If the exam wants you to do the steepest line and the shallowest line, then the worst fit lines, then that's all you need to do. So in order to get the gradient, the mean gradient, all you have to do then is get the average of the 2. So the steepest plus the shallowest and divide by 2. And that would be your mean gradient. Now, to get the percentage uncertainty, all you have to do then is divide the uncertainty by the mean gradient and then times it by 100%. And that gives you a percentage uncertainty in G. So this candidate here has beautifully laid it out. They have shown the working. It's really clear, okay? What I don't like with this though, okay, you're coming back here, 3, 2, 1, and is this actually 0? This is not good. This squiggly line at the beginning is not good, because you can read every part of that graph grid. So this will be 0.1, this will be 0.1. It looks like that this should be 0. So this bit here has been misread. They haven't read off the actual what this would be. Can you see that? So even though she's shown the working really nicely, actually the read off is out, and the read off can only be out by half a small square. So you've got to make sure that you are making use of the whole graph grid and label it up accordingly. So if that one's out, that one will be out. So actually, instead of getting 3 marks out of 3 there for showing the size of the triangle and the working, because they were, you know, read off wrong, just one read off wrong, and you suffice your mark. If you don't show your reading and think that you can be clever and not show it and just go straight to the answer and just give that, you don't get any marks. Okay, because the skill is here being able to read off from the graph the information that you need. Okay, all right. So then we go on to another 3 marks for, now if you have done that slightly wrong there, okay, you'll have to suffice your couple of marks, but the average gradient here then will be error carried forward from whatever you've got. So the average gradient here, nice working here and shown it, and the uncertainty shown it, and then the uncertainty calculated. Now the uncertainty, it should be to 1 significant figure. It doesn't start with a 1 anywhere, so we can just write that to 40%. We can write this one to 0.9. They're not going to penalise you if you do it to 2 significant figures, but it should be to 1 significant figure, unless it starts with a 1, and then it should be to 2 significant figures. But usually we don't stop there, do we? We always then have to go on with our gradient and use it into the next part. So when you're doing questions for data analysis, think, how are you using what you've just done into the next part? So you've worked out the gradient here, and then you might have to then say, for example, okay, not that bit. You might have to use it. Oh, okay, that's all right. Okay. You might have to use it to kind of like work out something else. So for example, from that mean gradient, you might have to go on with that and say work out G from that mean gradient. Let's just have a look back to see if we can see any relationship. I will just see if there is a relationship. So for example, G equals kx over m. Let's just say, all right, G equals kx over m. Okay, so G equals kx over m, where m, let's say, was the gradient. All right, let's just say x is a value that is given to you, say plus or minus, say 25 plus 0.0 plus or minus 0.1. So you can work out the percentage uncertainty of that. And k is maybe it's given to you. But what I'm trying to get at is whatever you get for your percentage uncertainty in your gradient m, you might have to take it forward into the next calculation to work out the percentage uncertainty in another value. So let's say they give you a value of x. Let's say they give you a value of k plus or minus, say 5%, or maybe that was hidden in a table, all right? You work out all of these percentage uncertainties because you're using them one each. Add all of those percentage uncertainties up to get the percentage uncertainty in G. Then you will have to work out what that the uncertainty in that value is. But can you see that it all ties together to use what you've been doing graphically to kind of like carry on to the next section? You shouldn't be having to do it afresh. You should be using what you've got from before and leading it on. Always look back to see what the clues are, because very often, for example, for WJC, they will leave the percentage uncertainties there for you in the table, all right? So kind of like carry that forward. Don't make up your own, all right? Use all the clues that you have been given. Okay, all right, and I think I just showed a relationship here, another relationship. But there are so many different ways that you can rearrange it to give you a straight line to relate it to y equals mx plus c. And as long as you follow it through, it's fine. But read the exam question, because the exam question might say, plot this against this. So they've effectively given you y and x. So you want to be using what they are asking you to do, even though you've got to do the maths behind it and relate it to y equals mx plus c. All right. Okay. Are there any other questions, Steve?
No, not at the moment.
No. Okay. All right. Okay. I think let's go back then to this table here. It looks a nightmare, but I don't think I did this. Okay. It's a nice table. It's a nice table, but we have to watch it. I know that the person who did this had problems because they couldn't take their kind of like lines out. But if they can't take their lines out, then they will have to put time taken in seconds for at the top of every single column, and then the mean time taken in seconds. So because every single column has to have a column heading with a unit separated by a separating mark. Okay, so this one, arguably, it doesn't matter about that one because they've got the column heading and they've got the units there. All right. Here they've said the resolution was to the nearest millimeter. It's a very, very easy mistake to make, but they've then actually done it to the nearest centimeter. Okay, so they've done 0.30 of a meter, which is 30 centimeters. So they haven't done it to the nearest millimeter. Now you could easily have a ruler that is plus or minus 1 centimeter, but read the instructions if that is the case. Okay. Otherwise, if you're saying that you can read to the nearest millimeter, then you have to have a 0 in that millimeter place. And it's no good putting another 0 on top of that, because you can't read to the nearest 10th of a millimeter. Okay, all right. The time here ties in because it's to the nearest 0.01 of a second. That's all beautiful on all of these, and it's consistent and it's the same. They've worked out the mean correctly to the same number of significant figures as all of the raw. That's fine, even though this is the least 2 significant figures, but the majority of them is 3 significant figures, so that's fine to go to 3 significant figures. Okay, majority of these, well, there's 3 on 2, 3, that's okay, 2 or 3 significant figures. Don't forget, you're allowed the same as the least plus 1. So you can have 2 or 3 significant figures here, all right? So this is fine, okay? And then when you calculate t squared from t, then it should be, if that's 3 significant figures, that goes to 3 significant figures. 3 to 3, 2 to 2, 2 to 2, 2 to 2. Same number of significant figures, look row by row, that is fine. All right, and then just to recap the uncertainty, all right, in any repeated readings would be you take the minimum one and the maximum one, and you take the 2 away from one another and you halve it to get this plus minus. Okay, what you're going up, what you're going down, and that's the uncertainty. But then to get the percentage uncertainty, you get that uncertainty and divide it by the mean time and times it by 100%. And we only need to quote it to 1 significant figure. Again, here, 1 significant figure, but if it starts with a 1, you can add another 1, and that's 2 significant figures. But then, if you want to get your uncertainty in t squared, because I'm using the time twice, okay, I can go 9% times by 2 to give us 18%. I times it by 2 because I'm timesing it by the power. If I had to do this time and square root, then I would be 9% times it by a half, okay, because the power of a root is to the half. Okay, all right. Okay, I think I'm going to stop there, sir, and Steve, and come back to you and you know, all of the comments are there, and I'll put it up on a PDF file for you later. Thank you very much for listening in.
Thank you very much, Jane Owen, for that. It was a comprehensive cover of data analysis there. Thank you all for listening. Join us next week.